do that.
Yeah, sorry about that. Or I can
It's
share
okay.
it from there.
Technical difficulties are part of any online thing.
Yes.
So here, I'll pull it up.
It timed out, so you know what? What do you think would work best?
I
Can you share
think,
time?
huh?
I just don't want to have to
Yeah, no, I can.
connect my iPad every time.
Yeah, no, I can share the game. And then we'll just transition to you, and I'll run through the game piece pretty quick. So that you can go through the problem. Yeah, this will be fine. Sorry, we're gonna take it down and then restart the game. Yeah, thank you guys for your patience there, and I'm gonna skip the first question. So I will go ahead and share my screen.
Can you share at the same time?
I don't think so.
Can you share now? I saw something the other day about being able to. There we go. Yeah, great.
Cool. So go to kahoot.it and then enter the game pin 72840. See, we had another person join, so they can join the game. Hold on, we're gonna do one. Would anyone else like to get in here? All right, I'm gonna go. And if you need to, you can join at any time. It's in the bottom corner. So I'm gonna go ahead and skip the first question. We'll move on to the second question.
Thanks, Trevor.
Yeah.
I think I'm gonna, I'll just do the problems on the whiteboard between.
Sounds good. So I will. All right. I guess get your answers in now that you saw it. Get those points. But this is like Whose Line Is It Anywhere, where the points don't matter, but you're all winners in our heart. All right. Cool. Right on. And we'll keep on going. Thank you guys for your patience. So the question. Oh, okay. Sammy, I'll let you. I was just gonna say, so flipping 3 coins, what is the probability of not flipping all heads? So what does that mean? Well, I know there's 6 of us, so playing the game. So when we see 6 answers, I'll go ahead and skip. But if you're still working on it, take your time. No pressure.
I think we have, Daphne told me we have 7 people now.
Oh, okay, cool. Right on, we got 7 8s, and I will pass it back over to Sammy.
Yeah, let's take a look at this on the whiteboard. Oh, not that whiteboard. I want a brand new one. Okay. So the question is asking, what if we don't get all heads? Thank you. Yeah, so there's two ways to look at this. We can use the property of negation, which says that, well, from the first problem, we found that the probability of getting all heads was 1/8, or we said 12.5%. And we know that probability always adds up to 100. Are you guys able to see what I'm writing?
Yes.
Yeah, okay. And we know that, probability is always 100%. So we can say 100%, or 1 minus 1/8 is going to be the probability of not getting all heads. And we're going to find a common denominator. So I'll do 1 times 8/8 minus 1/8. So then I have 8/8 minus 1/8, giving me 7/8. You could do the same process we did before to get it as a percentage, but I did want to show you how we got this answer, because there's actually going to be 8 possibilities, and we can look at it by grouping if it helps you see it. So the possibilities are that we get all heads, and order is important in this case. So we get heads, heads, tails, heads, tails, heads, or tails, heads, tails, or sorry, tails, heads, heads. I'm just adding a tails each time and I'm moving it around. You can do this systematically any way you want to check it, but we're going to end up with 8 possibilities, and you'll see that when we remove the probability of getting all heads, we're going to be left with 7/8. And then the final one is all tails. So this is 1, 2, 3, 4, 5, 6, 7, 8. And if we take this one out, we have 7 out of 8. Are there any questions? Okay. Let's move on.
Good job, Glad Possum. So the probability of passing chemistry is 60%, and the probability of passing bio is 70%. If the events are independent, what is the probability of passing chem or bio?
It's okay, Saka. You'll know that you got the right one in your head.
No worries. Like this is, like I said, a very kind of, we're just doing this for practice. This is just yeah, no stress. It's just a nice judgment-free environment to do some math together.
Okay, fantastic. So we'll take a look at this. And this one's a tricky one. So don't feel bad if you're a little confused on it. Okay, so the question was that the probability of passing chemistry is 60%. So I'm going to write that as P of C is equal to 0.6. And then the probability of passing biology is 70%. So I'll write that as 0.7. And then they want to know what the probability of passing chemistry or biology is. Well, and as Trevor mentioned, chemistry and biology are independent events, meaning they don't rely on each other. So there is a specific formula for that. And what we need are the probability of A or B. And we can write that for these events as a probability. I'm switching my letters, forgive me. B or C. So the probability of chemistry plus the probability of biology minus the probability of both of them happening. And this is where it's a little bit tricky. We care that they're independent, but they're actually not. Why does it keep deleting? Anyways, they're independent, but they're not mutually exclusive. Does anybody, how would you describe mutually exclusive? You want to shout it out?
I had a really good answer in the chat. Someone said no common outcomes.
Yeah, you're right. That's just really good. I like to view it as like kind of like a Venn diagram. Are you able to see what I'm writing, Daphne? How it cuts off? Is that better? I zoomed out. Okay. Yeah, if you're having trouble seeing it, you might be able to adjust your ratio. So these are mutually exclusive events because they have no overlap. But these are not because this little area in the middle overlaps. Anyways, so what we need to know is we need to know the probability of B and C. Does anybody know the formula for that? Okay. Well, the probability of both of them happening for independent events So I believe it's going to be the probability of B times the probability of C, which in this case will be 0.7 times 0.6, which will give us 0.42. So I'm going to plug these into this equation. So, and that's how we'll get the probability of B or C for events that are not mutually exclusive. My apologies for the delay. The way I had this originally set up, it would have worked a little more smoothly. Okay, so then we are ending up with 0.88, which was the answer. Do you guys have any questions? It can be a little bit confusing with independence and mutual exclusivity. So just let us know.
Yeah, it was helpful for me when I was looking at these problems is thinking of like, what do I do in the case of and what do I do in the case of or? And obviously that's going to be a little different depending on whether it's dependent or independent, but that helped me. And actually, when I was writing this problem, Sammy caught a mistake that I made when we were making it together. So yeah, if that one seemed tricky, it definitely was. Go next problem. Cool. Alrighty, now we're gonna play with marbles. Marbles are fun. Marbles are cool. Okay, so let's say we have 5 green marbles, 2 blue marbles, and 8 red marbles in a bag. Drawing 2 marbles with replacement. So that's a key. What is the probability of drawing 2 green marbles?
Okay, great. So there's most of you guys got it, but let's definitely talk about it. Okay, so, right, so it's asking, we have 5 green marbles, 2 blue marbles, 8 red marbles, and we want to add these up so that we know the total number of marbles will be 15 marbles. And so we're drawing 2 marbles with replacement, which is important because if you think of it as like the jar analogy, you know, we have 15 marbles in here. We take one out, we're going to put it back in. So the way we want to look at it is the probability of drawing 2 green. So it's going to be first the probability of drawing green with replacement times the probability of drawing green with replacement. I often set it up as, you've probably seen it with like these little placeholders so that we know what we're going for. So I like to write it as, well, the probability of green just by itself, if we're looking at that, is going to be 5 out of 15, which if we factor 5 out and simplify it is going to be 1/3. So I'm getting 1/3 times 1/3, which multiplied together is 1/9. And that was the problem. Any questions?
Right on. So now we're changing the situation slightly. So we have 5 green, 2 blue, and 8 red marbles in a bag. Drawing 2 marbles without replacement this time, what is the probability of drawing 2 green? How does that change the situation?
Okay, so it looks like everybody maybe needed some more time on this one. That's okay. Hopefully this explanation will make you feel more comfortable. Okay, once again, we have 5 marbles that are green. We have 2 that are blue, and we have 8 that are red, totaling up to 15 marbles in total. The idea of replacement or without replacement is important to how we think about it. So hopefully this doesn't take too long. I'm going to draw them in 1, 2, 3, 4, 5, 6, 7, 8. I won't do this for every problem, but maybe just this once. Okay, so that should total up to 15. So we want to know the probability of drawing 2 greens without replacement. So it's the probability of the green times the probability of the green, except these numbers are going to be different. For the first one, we have that there are in fact 1, 2, 3, 4, 5 green out of the 15 total marbles. And now here's where no replacement comes into it. I think I'll just exit out because it will be hard to tell if it's missing. So now for the next one, I want to know the probability of green, but there's only 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 marbles. So there's 14 marbles and only 4 of them are green. So the idea of replacement is you don't always have to draw it. You can just subtract 1 from the bottom, and you're usually subtracting 1 from the top. And these will not be the same fractions, 5 over 15 and 4 over 14, but we are going to multiply them together. And I think that I skipped a step when I was doing it. So 5 times 4 is 20. And then 15 times 14, well, you're going to be wanting to write it out, right? 15 times 14. And we'll do it the long way this time. 4 times 5 is 20. 0, carry the 2. 4 times 1 is 4. Plus 2 is 6. Here's my placeholder. And this goes away. So 1 times 5. And 1 times 1. And I will add these together to get 210. So that's going to be my denominator, but I see that they both have zeros. So I can make this more simplified. I'll take the zeros out and rewrite it as 2 divided by 21. What I did here was with the taking the zeros out was essentially I divided the top and the bottom by 1/10. And this was our final answer. Are there any questions about what it means not to replace it or anything in general? Okay.
So a box is painted 1/2 red, 1/4 blue, and 1/4 yellow. Throwing 2 pebbles, throwing 2 pebbles into the box, what is the probability that the first lands on blue and the second lands on red? Good job.
Okay, so do we want to move? Oh, we do have something.
There we
to
go.
do. All right. So just a little review here. We've got a box and it is painted half red. That's all red. And it's painted 1/4 blue and 1/4 yellow. I like to think about this similar to the coin problem, but without replacement, or with replacement, I'm sorry, because we can't actually remove a color from the box because it's painted on. So think about it as with replacement. And the way we see it is we want to throw 2 pebbles in, and what's the probability that the first will be on blue and the second on red? So this is the way I set it up pretty much every time for these kind of problems. I like to put those little lines out to know they're going to be holding something and there is multiplication in between it. So this red is 1/2, and this is 1/4, and this is 1/4. So the probability of blue, if we were to look at that by itself, is 1/4, which means there is, 25% chance that one of our pebbles will land on the blue paint. And now, because it doesn't remove the total, we're going to look at with the red. So that's 1/4. I'm sorry, 1/2. Okay. So basically, we're just multiplying these together. And that is how we get 1/8.
Yeah, I definitely want to mention what Daphne said. If you guys have any questions, like individual questions, feel free to send those to Daphne in the chat. Even if you want to keep it like a private message, just to just to ask things. This is literally for you, so we encourage any and all questions. Questions are good learning opportunities. So now we're going to change it up a little bit. So a box is painted 1/2 red, 1/4 blue, and 1/4 yellow. So throwing 2 pebbles into the box again, what is the probability that one is on blue and the other is on red? So not just saying the first one is on blue and the second is on red. Now we're saying, okay, just one is on blue and the other one's on red. So how does that change the situation?
Sure.
Sorry, I forgot. Just want to make sure we're getting attendance. I'll put that attendance survey in the chat after this one, but this is a good one. So, all right, let's take a look at this one. This was one of the harder ones for me as well. So
Okay, so this is actually pretty similar to the previous problem, except in this one, we care about order. Well, we care about order both times. But so I'm gonna quickly draw my little box again. But I'm just gonna label it like this. Okay, so previously we had the probability of getting first blue and then second red. And we found that by multiplying the individual probabilities in each like quadrant. So we had 1/4 times 1/2, which was how we got 1/8. But if we're looking throwing two pebbles where it's phrased as, what is the probability that one is blue and the other is red? Well, there are two options. There's a probability, we can think about it as first blue, second red, or we can think about it as first red, second blue. And what we actually have to do is we have to add these together. So from above, we have that first red, second blue is 1/8. And we can write the second portion as the probability of red times the probability of blue. It's actually going to turn out to be the same thing, but the important part is that we are considering the order from both directions. Sorry, that got a little bit off to the side there. So now we have 1/8 plus 1/8, which is going to be 2/8. And if we factor the 2 at the top and the bottom and cancel it, it's going to be 1/4. So that, yes, the tricky part about this question is the wording. The previous one, it only asked half of this question. This one is asking, well, what if order matters, but we don't know which one's going to be first? Do you have any questions?
The tricky one. Tricky. So a single light bulb has a 1 in 10 chance of staying on in 1 month. Given 3 light bulbs, what is the chance that they all stay on? Okay, good. So some of you guys got it. Some of you needed more time, that's all right. This one was also a little bit tricky. All right, so it says a single light bulb. A light bulb, that's a really bad light bulb, has a 10% chance of, or 1/10 chance of staying on. And given that 3 light bulbs, probability, given that
3 light bulbs, what is the chance that they all stay on? Okay, so I am going to do the method that I did previously, where I show all of the possibilities, and then we can kind of make, actually, these are independent events. So what we're actually gonna do is we're gonna do that little like multiplication setup once again. And we're gonna say the probability of each light bulb staying on all month is 1/10. So it's actually, you may have seen more complicated versions of this, but it's not as bad as some of them. So it's actually going to be the probability multiplied together. And there are other ways to look at it, but I think this one will be the most straightforward. Are you guys able to see? You're still able to see my screen, right? Great. Does anybody have any questions? All right, we'll move on.
So a single light bulb has a 1 in 10 chance of staying on the month. So similarly to what we've done before, given 3 light bulbs, what is the chance that they all go out? I think just in the interest of time, I'll skip forward.
Okay, this was a bit of a rough one. Everybody, and that's understandable. So basically what we're going to do is we're going to build upon what we found from the previous question, which said that the probability that a single light bulb will be on is 1/10. So now I'm going to look at the probability that a single light bulb will be off. And I am going to use the null occurrence formula, which says that it's going to be the total probability, which is 1 or 100%, minus basically the opposite thing happening. So I'm going to do 1 minus the probability that it's on. So it's 1 minus 1/10. I will find a common denominator. And I will get 10 minus 1 over 10, which is 9/10. So we're about halfway there. So far, we have found the probability that a single light bulb will be off, but we want to know the probability that all of them go out by the end of the month. And again, this is an independent event. The light bulbs aren't related really in any way that we care about. So I will do the probability that it's off for each light bulb. So like this is the first light bulb. This is going to be the second light bulb. The order is not really important here. I'm just explaining what these represent. And this is the third light bulb. So it'll be 9/10 times 9/10 times 9/10. Well, 10 times 10 times 10 is going to be 1,000. And then 9 times 9 is 81 times 9 again. We end up with 972. So we get 729 over 1,000. And that is not able to be simplified any farther because one of them is even and one of them is odd. And if we were to just test some numbers or check, at home using our calculator, we would see that it's no longer simplifiable. Are there any questions? This was the final result. That's a probability. It's pretty close to 70, I think it's going to be about 72.9%, if that helps you think about it. Okay.
So drawing a deck from a deck of cards, what is the probability of getting a pair of queens without replacement?
Okay, so something you may have only just learned for this class. I know I learned it almost specifically for this class. There are 52 cards in a deck. And within those cards, there are 4 suits. So like, you know, the heart, the club, the spade. Anyways, those aren't super relevant. The point is that there are 4 suits, and within each suit, there is 1 queen. So if we have 1 queen in each suit, that means there's a total of 4 queens in the entire deck. So now the question is, what is the probability of getting a pair of queens without replacement? Okay, so, well, the first thing we want to know is the probability of getting a queen just by itself. I'm going to put that as the probability of Q. So there were 4 queens out of 52 cards. We can simplify that later. But we want to know, you know, the probability of getting a queen and then another queen. So it'll be P of Q times P of Q, where these will not be the same thing. For the first one, we have 4 over 52, except I'm removing one of the queens. So now there's now only 3 queens, but I've also removed one of the cards. So there's now 51 cards. So that's how I like to think about it. As I mentioned before, we subtract from the top and we subtract from the bottom. And this is going to be how we get the probability of getting a pair of queens without replacement. That's specifically what's happening, no replacement. And then I believe we can simplify this a little bit farther. Yeah, but let's distribute this first. So 4 times 3 is 12. 52 times 51, since we aren't using calculators. And we'll add this together to get 2, 6, 5, 2 on the bottom. Obviously, we want this to be fully simplified. And I believe we can actually divide 2, 6, 5, 2 by 12. I know this is a bit of work, but since this is what you'll be doing on your exam, I think it's probably a good thing to show some of it. So my first question is, how many times does 12 go into 26? Well, I think 2 is good, because then we'll have 24. And then we have 2, 5, 2. I'm going a little bit fast. Please let me know if you want me to slow down or emphasize more. So basically I subtracted the 4 from the 6 and I got the 2, and then I brought the 52 down. Now I ask myself again, how many times does 12 go into 25? Well, once again, it's 2 times. It's nice, we get to choose what numbers we want to work with almost. Got a 1 carried down, the 2 goes into it exactly 1 time. This is perfect. This means that I have a remainder of 0. So when I write the number of times that 12 goes into 2,652, what I'm doing is I'm factoring that 12 out. So I can write the 12 on top, carrying it, and then I can write 12 times 221. And then these 12s will reduce. So my final probability as a fraction is 1 divided by 221. And that was the red box, and that was the answer.
All right, so let's find the sensitivity. So we want to find the sensitivity for this graph. Let me see if I can zoom in here. So I know you can't see the answers. So if you want to write down the answers first. So 9,000 over 14,250, 9,000 over 15,000, 2,970, 750 over 35,750, and 29,750 over 3,500, I mean 35,000. If you can't see it, I can continue to zoom it in. Nice. Good job. You guys know your sensitivity.
There you go, guys. But we will go over it just really briefly. Besides, it's going to build on itself. So we'll probably use the same results again. Okay, so just for reference, I'm going to draw this table, but we're going to be using it if there's future questions that we need help on. Okay, so that has the disease, does not have disease, and we'll call this the total. And then over here, we have the people that test positive and the people that test negative. I really overestimated the amount of space I would need. It's okay. And then we have the total. And as we go through each of them, let's talk about what they mean, right? So this 9,000 here, this is what we call the true positive, meaning they test positive and they have the disease. Okay. And then below that, this is not anything specific. At the bottom, we have 15,000, and we call this, the total with disease. And then we have the people that test positive but don't have the disease. This is the false negative, right? Or false positive, I'm sorry. Yeah, so the 6,000 was false negative. I don't think we end up using these in any of our formulas, but it is good to know that this here is a false positive, and this one is a false negative. Here's a useful one that we're often asked about. So they test negative and they don't have the disease. This is what we call a true negative. That's the total that does not have disease. And again, I'm just setting this up because there's some questions coming up that we will be continuing to reference this chart. We call this the total that test positive or the total positive. This is the total negative. And then we have the total overall, which is the number of participants in the study or the number of people that we're looking at. So that's set up for future use and for our current use. We were curious about the sensitivity, which is true positive divided by the total that have the disease. And now some of you may have memorized this as like different letters, and that's totally fine. I personally prefer to be able to identify the areas on the chart and then just know it by this definition. So you can use whatever works best for you. But we have already identified the true positive up here. So that is 9,000. And we've also identified the total that have the disease down here. So that is 15,000. And we can simplify that a little bit, but they didn't do that in the example, which makes sense because we are talking about whole people. So you could think about it either way. You could, divide the zeros out and you could get 9/15, or you could have gotten the original, which was 9,000/15,000. Did you guys have any questions? I know most of you were pretty good on this one.
Cool. Yeah, and the I guess a little comment there is usually they'll be looking for sensitivity and specificity in terms of a percentage. It's almost like, yeah. So just letting you know that we kind of kept it this way because we figured calculating it was probably the important part. Here, so I'll share again. I do want to mention, just because we have a little bit of time left, I'm going to put the attendance survey back in the chat. Please, please, please fill that out so that we can continue to host stuff like this. I see I got like 3 responses, so if you could take just a moment to put in your student ID, that'd be great. And I will go ahead and share my screen again. Nice. So same table, but finding the specificity. Yeah, and if you can, try to do these from memory. Try to, I know you probably have access to your notes at home, but use this as an opportunity to kind of test yourself. Good
Fantastic.
job.
And very briefly, we already have the setup. Yep, here we go. Great, so we already have a lot of the information we need. And now the question is about specificity, which is defined as true negative divided by total that don't have the disease. Okay, so the true negative is right here. It's at the end of that arrow. So we have 29,750. And we're dividing it by the total that don't have the disease. That is represented at the end of that arrow, 35,000. And that was how they left the answer. But as Trevor mentioned, you could also do it as a percentage.
So find the PPV, the positive predicted value. Nice.
All right, I'm pulling it up. Okay, so I don't know if I read off to the side here. Okay, yeah, so I guess you guys can't really see it. So I'll just replace where I've got sensitivity. And that's where we'll talk about PPV, which is defined as the true positive, or the amount of true positives divided by the total that test positive. I've seen like some of your homeworks, it can be a little confusing, the definition. I think they leave out the part that says test, they just say total positive. That may be something you may want to be aware of when you're thinking about it. So you don't mix it up with a different value. Conveniently, everything's already labeled. So true positive is 9,000, and the total that test positive, where my error was just now, is 14,250. And that is that.
And the NPV. Nice.
Nice. And there was a little bit of confusion there, so we'll just finish that up. If you want me to spend more time on this page where I've labeled it, please let me know. That is pretty important to the understanding of it. So I'm just going to put it where I had the other value. Negative predictive value is defined as the true negative, which is negative the test negative divided by the total of the test negative. And so we've got everything already determined. So the true negative is attached to that arrow, and the total of the test negative is attached to that arrow. So we end up with 29,750 divided by 35,750. Were there any questions on this kind of problem? Identifying what things mean? Okay, all right. I'm gonna assume you guys are very confident in it, which is awesome. I'm really glad.
So suppose 100 out of 1,000 people have a disease. Suppose the test has sensitivity 95%. How many true positives are there? So we're getting away from the past table. This is new information. So what you get is 100 out of 1,000 people have a disease, and the test has sensitivity 95%. We want to find true positives. All right.
So that went fairly well for most of you guys. All right, so we have previously stated that the sensitivity has a definition of being a true positive divided by the total that have the disease. And we said that that is equal to 95%, which I'm going to put as a decimal 0.95. Well, I like to make a little chart. We'll at least make part of it. So it has the disease, tests positive, tests negative, total. You guys know what goes everywhere else. Hopefully we won't need it. Share the file. Okay, great. Thank you for sharing that, Trevor. So basically, we have that there are 100 people out of 1,000 people that have the disease. So down here at the bottom where it has the total of disease, that's where we're going to put 100. And we also have 1,000 for the total number of people. And we said that the sensitivity was 0.9%. So what I'm going to do is I'm actually going to substitute in the total that have the disease that will allow me to find the amount that's the true positive. So I'm gonna just follow this over here. We have the true positive divided by the total of the disease, which is 100. So if I were to try to solve, 0.95 is equal to the true positive divided by 100. I will multiply 100 to both sides. So that will give me 95 is equal to the number of people with true positive, which I believe is what they were asking. How many true positives are there? Okay, thank you. I know we are running short on time.
Yeah, so we're about out of time for today, but I did want to mention, so in the chat, I put the list of question and answers. If you guys want to keep on going through some questions from like the homework, and like basically you can treat it as just practice problems to get prepared for your exam. It has the solutions. It says which are the solutions. If you have any questions on them, you can always come into the STEM Success Center. So we'll be tutoring all throughout the week, 10 a.m. to 5 p.m. Monday through Thursday, and then 10 to 3 on Friday. So our tutors can also help you out with these questions there. Did you guys receive a study guide yet? I believe you're going to. Did anyone receive a study guide yet? Well, check your Canvas. So you should be receiving a study guide this week to help you prepare. So just more practice, the better. But I really I wanted to thank you guys for coming and for being so participating, asking questions and answering in the chat. That was really helpful. Guess a big we'll give Sammy a big hand. Get it? A big hand. No, but
Thank you.
thank you so much.